This video, we are going to see the maximum power transfer theorem and how to apply maximum power transfer theorem to a linear bilateral network. This is a part of circuit analysis. You can apply this theorem on any bilateral network, either to a DC network or to an AC network. So when you are applying this theorem to a DC network, then the maximum power condition changes. When you are applying this for an AC circuit, then the maximum power condition changes. Okay, so let us have a look at the objectives. First, we are going to define what is a maximum power transfer theorem. We are going to state maximum power transfer theorem and explain by taking one small example, and we will apply that on a given circuit. After that, we are going to see the proof of this particular theorem. So let us start with the statement. Maximum power transfer theorem states in any linear bilateral network that may be a DC network, an AC network. As of now, we consider DC network. Maximum power will be delivered to the load if the load resistance is made equivalent to the Thevenin's equivalent resistance. We know how to find the Thevenin's equivalent resistance. So Thevenin's equivalent resistance is the resistance found by replacing the voltage sources and current sources with their internal impedances. Okay, so when it comes to DC, if the load resistance is made equivalent to Thevenin's equivalent resistance, then the maximum power will be delivered to that load. In the case of AC, in order to deliver maximum power to the load should be the complex conjugate of the Thevenin's equivalent impedance of that network. Complex conjugate of the Thevenin's equivalent impedance of that network. So these are the two statements, one with respect to DC, the other one with respect to AC. We know the power delivered to the load formula, power P is equal to IL square into RL. If you know the current flowing through the load and load resistance value, so IL square into RL is the power. Okay, let us see the explanation of this maximum power transfer theorem little more elaboratedly. We take a network may contain any number of voltage sources, any number of current sources, resistors connected in any manner, that is this network, and RL is the load resistor connected to the same network across terminals A and B, right? So according to Thevenin's theorem, we can replace this entire network with a voltage source in series with equivalent resistance RTH. So if you replace this network with Thevenin's equivalent network, the network will take the shape like this. So which will have VTH, RTH and RL all in series with each other. So in this particular network, if you apply KVL, you will get the value of IL as IL is equals to VTH by RTH plus RL, where IL is the load current flowing through the load resistor, and RL is the load resistance value, VTH is the Thevenin's equivalent voltage or open circuit voltage, RTH is the Thevenin's equivalent resistance found by replacing the voltage sources and current sources with their internal impedances, right? So power delivered to the load PL is equal to IL square into RL. We know the formula for IL. IL is equal to VTH by RTH plus RL. We substitute that one here, and according to the maximum power transfer theorem, maximum power will be delivered to the load if this RL value is equal to RTH. So what we do is we substitute RTH in place of RL You substitute RTH in place of RL in this formula, we'll get the power formula PL, the power delivered will be maximum. So PL maximum is equals to VTH by RTH plus RTH, because RL is equal to RTH, only then power will be maximum. So into RL is equal to RTH. So if you simplify that, you will get VTH square by 4 RTH. So this is what is the power delivered formula, or the maximum power delivered formula, by applying the maximum power transfer theorem. Let us try understanding this concept little more thoroughly with two examples. So one is this one, the second one is this one. Here we changed RL values. Here RL value is 15 ohms. In this circuit RL value is 3 ohms, but remaining all the parameters are same network is considered here in the first example. In the second example also we have considered the same network, but only difference is here RL is 15 ohms, here RL is 3 ohms. We know the formula for IL. IL is equal to VTH by RTH plus RL, and we know the formula for power P is equal to IL square into RL. PL is power delivered to the load, so load current square into RL. So here substituting the values of VTH, RTH and RL in this formula, we got the power delivered to this 15 ohms as 15 watts. The unit for power is watt. So 15 watts power is delivered to this particular resistor. Now you see this particular thing. Here I have considered RL is equal to RTH. RL is equal to 3 ohms, whereas RTH is also 3 ohms. So if RL is equal to RTH, our source resistance, then according to maximum power transfer theorem, this load resistor should receive maximum power from the source. Let us check whether it's going to receive the maximum power from the source or not by substituting the values of VTH, RTH and RL value in this formula. Then we'll get PL is equal to 18 by 3 plus 3 RTH plus RL whole square into RTH. So that is 18 by 3 plus 3 whole square into 3, that is 27 watt. So when you compare this power and this power delivered will be more if the power delivered is more here, though the resistance value is less. So it is very clear that if load resistance is made equivalent to Thevenin's equivalent resistance, the maximum power will be delivered. Right? Let us apply this on another circuit. In the given circuit, find the value of RL. We are going to find the value of RL such that the maximum possible power will be delivered or transferred to RL. Okay. So what we have to do is, in order to deliver maximum power to this load resistance, so RL should be made equal to RTH. In order to find the RTH value, what we do is we remove the sources. We remove RL first. We remove RL from the network, and we replace the voltage sources or current sources with their internal impedances. Here the internal impedance of this voltage source is not given, so we replace that with 0. So now after observing carefully, this 3 ohm resistor and these 3 ohm resistor both are in parallel. 3 into 3 by 3 plus 3 is the equivalent resistance of this combination, that is going to be 1.5. That 1.5 is going to come in series with this 2 ohms and this 1 ohm. So the Thevenin's equivalent resistance, or else the equivalent resistance of this entire network, is going to be 4.5 4.5 ohms. So if you consider RL value to be equal to 4.5 ohms, you will notice the maximum power delivery to this load resistor, right? So this slide is going to give you the proof of the maximum power transfer theorem. Okay, RS is nothing but RTH, Vs is nothing but the Thevenin's equivalent value, and RL is the load resistor. This is the formula for power. In order to get the first maxima, we differentiate it into we differentiate this equation with RL and we'll equate it to 0. Then we'll get the condition for the maximum power. So are the first maxima. So by doing so, if we differentiate this with respect to RL and equate that value to 0, then we got the condition as RS is equal to RL. That is, if load resistance is made equivalent to Thevenin's equivalent resistance, then the power delivered will be maximum. It is proved. Okay. So now, after the completion of this particular video, student will be able to define the theorem and explain the concept of maximum power it delivered, when it will be delivered, and he can prove the theorem and he can apply the theorem concept to a bilateral networks in order to see the maximum power, uh, in order to check the condition, in order to apply the condition when that particular maximum power will be delivered. Thank you.